So today what I'd like to do is look at the Earth's atmosphere. We'll look at some basics of air pollution, and we'll look at the scales of air pollution to provide a framework for what we will consider for the rest of the semester. So this is a fairly complicated figure. It's got a lot of information on it. So let's just kind of go through, and it describes or presents the atmosphere. So what I want to do is look here. So basically, let's look first at the troposphere. So the troposphere contains about 70 to 80% of the entire mass of all of the Earth's atmosphere. It extends up to 8 to 6 kilometers, depending on the location on the Earth. And the jet stream and all of the weather occurs in the troposphere. So the jet stream occurs in the upper regions of the troposphere. We spend all of our lives in the troposphere, and you can see here showing sea level, Mount Everest within the troposphere, clouds within the troposphere. If you fly, you're still within the troposphere. The next layer is the stratosphere. Switch some colors here. And so here is the stratosphere. Now, where you hear about the stratosphere has to do with ozone depletion, and we'll talk extensively about that. This stratosphere ranges from about 20 to 40 kilometers above the Earth's surface. It is deeper at the poles and thinner at the equator. So if we look here, okay, that ozone layer occurs in the stratosphere. Supersonic jet is also travels within the stratosphere. Above the stratosphere, we have what's referred to as the mesosphere. So here's the mesosphere. It ranges from 40 to 80 kilometers above the Earth's surface, and meteorites burn up in the mesosphere. Above the mesosphere is the thermosphere, and the thermosphere ranges from about 80 to 500 kilometers above the Earth's surface, and ions reflect radio waves back to Earth in the thermosphere. So the space shuttle, we find that in the thermosphere. The aurora borealis occurs within the thermosphere. And then lastly, we have the exosphere. So now we're well above the Earth's surface, the outer regions of it. We have what is nearly a vacuum in the exosphere. And here is where you would find the Hubble Space Telescope, artificial satellites, space probes. So those are located in the exosphere. This plot here gives answering a quick question. This plot here gives a temperature profile. There's actually a temperature profile in that previous slide, but this one shows it a little bit. I think it's a little easier to observe. As you probably noted, when you flew, if you watched the screen with the temperature gauge, as you increase in elevation, the temperature decreases. And then that's what we're showing right here. So we can see this temperature decrease. So within the troposphere, as elevation increases, the temperature decreases. Now, when we get to the stratosphere, the opposite is true. So here, as the temperature increases, sorry, as the altitude increases, the temperature also increases. Anyone have any thoughts of why that is the case? Why would you see an increase in temperature with increasing elevation?
Is it because the hot air rises?
Hot air does rise, okay, but remember, it's really cold. We're down to about minus 50 degrees at what they call the tropopause, that change between the border between the troposphere and the stratosphere. So while that's true at that point, that the temperature there is extremely cold. So why might, in this case here, temperature increase with altitude?
Is it because pressure is decreasing?
Pressure is decreasing, okay. What happens, when I mentioned the stratosphere, when we think of the stratosphere, is there any chemical we tend to think of being important?
Is it because of the ozone layer's presence?
Exactly. It's because when ozone reacts with light, it gives off, and the higher in elevation, the more UV radiation there is, the greater those reactions, so the more heat that's generated. So that's why there's an increase in temperature with elevation or with altitude in the stratosphere. And then when we get to the mesosphere, now again, temperature is going to decrease. And then the opposite is true in the thermosphere. Once we get out to the thermosphere, the temperature is rising, air molecules are few. Temperature really, once we get to the thermosphere and the exosphere, temperature really has very little meaning because the density is so low. The concentrations of air molecules are so low. Really what you're looking at there when we're looking at temperature, it's really, we're looking at vibrations of those molecules that are there because of the radiation. So density increases, and that's true across. We'll look at it in the next slide here. So density consistently decreases with altitude, but the temperature is variable. The change in temperature is variable because of the difference in the reactions. And that's true even in terms of the chemical reactions that occur. But if we look here, and what we're looking at here are the reactions that involving chlorofluorocarbons. So chlorofluorocarbons, for instance, Freon, we'll talk more about these later, but these were released into the atmosphere. They're important, and we'll see later in terms of how they affect the ozone layer and the ozone concentrations in the stratosphere. But you can see that the reactions are different on land versus in the troposphere versus in the stratosphere versus in the ozone layer. So in the ozone layer is in the stratosphere, but there's additional reactions in terms of what happens with those reactions involving ozone. So those are important. They govern all of these air pollutants, the concentrations of air pollutants. They also, as we'll see, they also govern the effects of these air pollutants. The other thing that's important, and we'll consider, are the effects of the sun rays on both the concentrations of water vapor and the strong currents that are produced. So all of you can see it here. We see that it's referred to as the Hadley cell. It's a mid-latitude cell, polar cell. These movement of air results because of the radiation from the sun's rays. If it wasn't for the sun, you wouldn't see these different currents. And this results in the jet stream, and as I mentioned, it results in all of these various cells. That produces weather patterns, that changes the meteorology, that affects how pollutants move in the atmosphere. Now, the vast majority of the atmosphere, and we're really looking at this point in the troposphere. Most of what we will look at this semester will be in the troposphere. When we look at ozone depletion, we'll look at those reactions in the stratosphere. But because we're concerned about the effects on both humans and the environment, we exist in the troposphere, so that's where we focus our effort. The vast majority of the atmosphere is made up of nitrogen and oxygen. Only about 1% is everything else. Now, water vapor does vary significantly. It varies from about 0 to 4%. I've noted some of these in red. Anybody have an idea why did I choose to denote water vapor, carbon dioxide, methane, and N2O in red?
Are they greenhouse gases?
Exactly. They are greenhouse gases. Okay. Those in blue are inert gases. So we're very much concerned with the concentrations of especially CO2, methane, and N2O. We're worried about water vapor, and we'll talk when we talk about greenhouse gases. You'll see that none of the models that have been developed to predict the effects of greenhouse gases on the environment are effectively predict these effects without water vapor. We need water vapor. It's much harder to control it, and it's much more variable in the atmosphere. And we can see that in this next image, which is a graphic showing the concentration of water vapor in the atmosphere. Anything you note from this video?
It's more present at the equator.
Exactly. Okay, so one of the things is that water vapor is concentrated at the equator. You can see at the polar regions, they're extremely dry. Antarctica is essentially a desert. Receives very, very little rainfall. So, and you can see if we play this again, the changes with season. So you can see how during the monsoon season, the concentrations, for instance, around India increase significantly. So these play a significant role also in especially the transport and also the reactions of the air pollutants. Okay, let's look at some sources of air pollutants. And I like this figure because it just gives you some sense of the different types of pollutants. Let's look first at natural. So you can see from here, mentions lightning, volcanoes, wildfires, and even forests. So if we're looking at, for instance, forest fires, what are some of the pollutants, or what are some of the chemicals? I haven't defined pollutants. I keep using it. We will talk about it in just a little bit. What are some of the chemicals that you think might occur from, for instance, from forests in general. And you can
Are you
think.
talking about when they're burning?
Nope, I'm talking about just forests.
Oh, okay. Oxygen?
So, okay, trees produce, give off oxygen. What else?
They store CO2.
They store CO2. They actually give off CO2 at night. They respire. What else? Do they give off anything that is particulate, that is a solid?
Do they give off water vapor?
They give off water vapor. They definitely do.
Pollen?
They give off pollens. That wonderful green deposit on our cars in the springtime. Make us sneeze, right? What else? Has anybody been to the Smoky Mountains?
Yeah.
Yes.
Are they smoky? Do they have kind of a hazy appearance?
Yeah.
Why?
Sort of.
Sort of? Why?
Would that be the result of all those pollutants that are getting emitted?
It's actually the result of volatile organic chemicals. So they give off a variety of organic chemicals, and those and it's naturally occurring, and those organic chemicals they refract light and they cause that hazy appearance. How about volcanoes? What do they give off?
A lot of carbon.
A lot of carbon. So the forest fires, right? So they give off carbon. What else?
Do volcanoes give off methane?
Volcanoes actually give off both methane. So this is from the volcano. They also can give off H2S. Anything else?
Water vapor?
They give off water vapor. When we talk about carbon, it's often we refer to it as carbon soot. So it's a particulate, and we'll talk extensively about particulates. They can also give off SO2. Any other naturally occurring source of pollutants? Not sure what I just did there. Oh, I know what I hit the link. Apologize. Okay, dust storms. Significant amount of particulates, depending on what is sorbed or attached to those particulates. Pesticides, herbicides, heavy metals, those then get transported in the atmosphere. Now, we also talk about mobile sources and stationary sources. So mobile sources are cars, trucks, buses, motors, anything that is powered. Now, give you this is a portable asphalt processing plant. So, if you're paving a highway, is that asphalt processing a mobile source or a stationary source? It's kind of a trick question.
That would be stationary, wouldn't it?
It's stationary because it's not powered itself. So it's actually considered, even though it is mobile or it moves, it can be transported, it is not a mobile source by definitions under the Clean Air Act. So it's considered a stationary source. So stationary sources emit a relatively constant quantity of the same pollutants unless you change the process. Typically, they're going to have some sort of a pipe, and out of that pipe, emissions flow. So they can be shown here: industrial, manufacturing, power plants, sewage treatment. We don't think of sewage treatment necessarily, maybe, as a stationary source. So why is sewage treatment plants included here? Unfortunately, in 483, we actually didn't get to go to one. If we had, you probably would have realized it.
Is it because
Right.
water vapor gets evaporated off from the wastewater?
So water vapor does get evaporated from the wastewater. We often aerate that wastewater. And if you aerate the wastewater, you produce aerosols. So, and you can release volatile organics. So if you are anywhere near a sewage treatment plant, especially in the summer, you know it smells. So it releases an odor. Well, that odor is resulting from those organic chemicals or methane, sorry, not methane, hydrogen sulfide that is released. It also will release methane, but methane you won't smell. You will smell hydrogen sulfide. Now, also listed here are area sources. So think of these as not having a pipe out of which emissions flow, analogous to in water systems, non-point sources. We tend to talk about these as area sources. So you can see from shown here, the farmer fertilizes the field. Some of that fertilizer volatilizes, ends up in the air. Got a confined area feeding operation or a CAFO. Got a lot of animals. They're going to produce methane, hydrogen sulfide, and that can be released. So we put some methane here. We'll put some hydrogen sulfide, perhaps from our captain. So again, we have some more VOCs that are released. Can you think of any other area sources? Shown here, a city. What else might be considered an area source?
Could it be like landfills?
Could be landfill. Okay. So a landfill kind of depends on if the landfill has a pipe, then it's typically considered a stationary source. But if it's open, so an open dump would be definitely an area. And thankfully, we don't have open dumps in the US, but elsewhere in the world they exist. What else? It's wintertime. We put a house here with a chimney.
CO2 from burning wood.
Exactly. It could be CO2 from burning the wood. It could be particulate matter from burning wood, oil. It could, in areas where coal is still burned, it can be SO2 from the coal burning. So there's a variety. You've got a area with multiple houses, and those then are considered, they're not typically not considered a stationary source, they're considered an area source. They're much harder to regulate. It's easier to regulate one power plant. It's much harder to regulate 5,000 houses and what they are actually emitting. So it's harder to regulate an area source than a stationary source. Could be backyard grilling. Summertime, everybody's out there grilling. That's releasing various different pollutants. It can also be oil and gas drilling, which releases pollutants. And typically that's considered, because there are multiple locations, it's considered an area source. So I've used the term air pollutants. Let's really define it. And what we're talking about is any substance in the air that in high enough concentrations produces a detrimental environmental effect, and that includes health. So for instance, in order for the US EPA to regulate greenhouse gases, they had to make a determination that CO2 was a pollutant or is a pollutant. And in order to do that, they had to demonstrate that CO2 has a detrimental environmental effect. Without that, there was no way under the Clean Air Act to regulate CO2. So that determination is critical in developing any sort of regulations. When we talk about air pollutants, we talk about primary standards and secondary standards. Those of you that have had 483, when we talk about primary standards with water, we're talking about enforceable standards. When we talk about secondary standards, we're talking about non-enforceable standards. Secondary standards with water have to do with aesthetics. Primary standards with water have to do with health effects. In air, primary and secondary standards are both enforceable. So the primary standards are based on human health, and secondary standards are based on impact on the environment and property, but both are enforceable. We also talk about primary pollutants and secondary pollutants, and I'm just gonna, can you see the bottom of my screen? Because on my secondary computer, I can see primary pollutants, but I don't see secondary pollutants.
We can see it.
Okay, good. So primary pollutants are released to the environment. So these come out of a smokestack, for instance. They're the aerosols or the volatile organic chemicals that are released from the aeration tank on a wastewater treatment plant. They're the combustion products, so the particulates, the soot, the CO2 that are released from burning. Secondary pollutants are generated in the environment. So these are actually formed in the environment. So for instance, we'll talk more about this later, but there's a variety of chemicals. So for instance, volatile organic chemicals that are released, NO2 that is released, plus water vapor, plus the sunlight react to produce ozone. In this case, we're looking at ozone in the troposphere. So when we talk about ozone, we'll talk both about ozone in the troposphere, and we'll talk about ozone in the stratosphere. And they're very, very different. Now, when we talk about particulate matter, we're talking about solid particles. It can be fiber. So this is actually an image of asbestos, which forms these needle-like fibers. It's one of the reasons why asbestos is so toxic, is because you can imagine these needles in your lungs, they basically puncture these cells. We can talk about gases. We've talked about ozone. We've talked about CO2, SO2. We can talk about NO2. We can talk about lead. All of these are gases that are released to the atmosphere. We can talk about liquid particles. When you sneeze, see the particles. Those are liquid particles. And we'll often talk about aerosols, which is a suspension of solid and liquid particles in the air. It includes all of the vapor and gas phase components of the air, but it's a suspension of solid or liquid particles. And we're going to talk about liquid particles, so those liquid droplets that are formed and are present in the air. So when we talk about particulate matter, we've mentioned some of these in terms of how they are produced. We've said combustion. So we talked about particulates, that carbon soot that's produced in ash, from cars, trucks. You see a exhaust system on a car that's not working properly, and you see that black soot. That's the carbon soot that's produced from incomplete combustion. What else can produce particulate matter? We've mentioned some of this.
Volcano eruption?
Volcano eruptions,
Soil erosion.
soil erosion.
And pollen too. Does pollen count?
Yep, pollen counts. It's a particulate matter.
Farming.
Fireworks.
Fireworks. Farming can, especially during tilling. Anything else? Mechanical grinding, sandblasting, is going to produce particulate matter. We'll talk about occupational hazards. And there, so for instance, in certain factories, for instance, in a sugar factory, in flour producing, in aluminum processing and manufacturing, that aluminum is ground very, very small to produce dust. So these can produce particulate matter. So how is particulate matter removed from the atmosphere?
It settles?
Okay, sedimentation. Any other ways?
Filtration.
Can be from filtration, especially in terms of when we're looking at control technologies. Can also be filtration. You can get some filtration, for instance, through trees. That basically they act essentially almost like a filter. Building, you're in a older community, Pittsburgh, for instance. We mentioned Denora. The buildings are kind of the black coating from black carbon. What happened? So carbon, those particles impact that surface and actually then they stick there. Talk about part of impaction and agglomeration. And we can also talk about washout. So there we're talking about it rains and that helps to wash out the particulates. Now, when we talk about particulates, we talk about PM10 and PM2.5. The 10 has to do with 10 microns, so they're particles 10 microns in diameter or smaller, and particles that are PM2.5 are particles that are 2.5 microns in diameter. Give you a sense of what we're talking about. A human hair is 60 microns in diameter. So PM10 is 1/6 of that. And PM2.5 is 1/30 of that. So these are extremely small particles. We differentiate in size because of the effect on the respiratory system. So particles that are smaller are going to get deeper into the respiratory system. So we worry about it, or we try and control it and prevent human disease or the environmental effects based on this size differentiation. We can also talk about the scale of pollutants. So we can talk about a local scale. So let's look at, we were in a normal year and we were all on campus. We look on that local scale, we're looking at typically one or several large emitters or a number of small emitters. So we'll look at air pollution on the MSU campus in a normal environment, normal academic semester. What are some of the sources of these pollutants that we
The catabuses.
catabuses? And they're going to produce, for instance, NO2, carbon monoxide. They might particulates. What else?
The MSU power plant.
Power plant. And there when we burned coal, SO2 was emitted. There's SO2 emissions are reduced significantly now that we use only natural gas. So this is much less now, but there's still carbon monoxide, carbon dioxide, and various forms of nitrogen oxides. Any other sources?
All the farms.
So the farms. So we've got various different VOCs, we've got methane, we've got H2S. Other sources. Do we only have buses on campus?
Commuters.
Commuters, all those cars, trucks. And we've got the same thing. NO2, carbon monoxide, particulates. What about, do we have any building construction? We have particulates from that. And so we have a variety of sources. So we're looking here at what occurs at the local level. We can look at air quality. This is actually for Lansing, that we don't have air quality measurements for MSU, but you can see here, we can actually look at the ozone levels, we can look at the particulate levels, we can look at NO2, you can also look at SO2 levels, you can look at it over time, you can look at it seasonal changes, but we're really looking in this case on a local level. We can also look at an urban level. So here, typically what we're looking at is, because we're looking at a larger area, those primary pollutants are released. There's more time for the reactions to occur. So now you're looking at the formation of secondary pollutants. And typical sources are essentially the same as local. Here, when we're looking at urban, we're often looking at the formation of photochemical smog. Again, because we have sufficient time for reactions to occur. Now we can also look at regional. So for instance here, if you were to look at the East Coast, you'd have Boston, then you have New York City, then we've got DC and Baltimore, and basically we could look at each one of these as an urban pollution, but then we could look at this as on a regional level. We can also look at it on a regional level. If we look at Lake Michigan, so this is Lake Michigan, we have Chicago over here, and we have Holland, Michigan over here. Got lots of pollution from Chicago. We've got predominantly westerly winds, so we've got winds moving from the west towards the east, towards Holland. And in the summertime, those chemicals that are released, the VOCs, the NOx, basically bake over Lake Michigan. Lake Michigan acts as like a mirror. They bake over Lake Michigan, and then what happens is we have ozone formed on the west coast of, or the east coast of Lake Michigan, the west side of the state. And from a control perspective, it's much more difficult because that ozone is produced from chemicals released from across the lake, from in an entirely different state. So it's really important when we talk about pollution and controlling pollutions that we look at this on an interstate or a regional level. We can't control the concentrations of Holland or concentrations of ozone in Holland without looking at Chicago, Gary, Indiana, etc. Same is true with acid rain. We'll talk about that. There, SO2 is released. It reacts in the atmosphere. It produces sulfuric acid. That sulfuric acid falls to Earth and causes harm to both humans and the environment. And then we also can talk about haze or visibility, and you can see that in these figures here. These are taken at different national parks. One of the things that you note if you look at haze, it varies in properties or the chemical composition in different parts of the country. So how we deal with that from a control perspective is very, very different. So the red is sulfates. You look at Shenandoah National Park in Virginia, sulfates contribute to much of the chemicals that cause haze. On the other hand, if we look at the Badlands of South Dakota, it's a combination of sulfates and nitrates shown in yellow, and then, or some other chemicals. And then if we look at Yosemite, it's predominantly a mixture of sulfates, nitrates, and organic carbon shown in blue. So again, how we deal with these from a control perspective will vary depending where we are in the US and what the causes or sources of these pollutants are. We also can look at air pollution from a continental perspective. So for instance, shown here, we have coal burning in Poland, in the Czech Republic. That air moves northward, and then Sweden and Finland are affected by this pollution. In the US, we had a significant amount of coal burning. In the Southeast, those chemicals then move, they're transported into Canada. So Canada is dealing with our pollution. Same Taiwan, deal with pollution from China and Korea. Fires in Australia affected the air quality in New Zealand. So this becomes much more difficult in terms of how we actually deal with these pollutants. And then we can look at global, and now we're looking at really long range transport. And just let me finish this last slide. So shown here is from the Chernobyl accident in 1986, and you can see that radioactivity resulting from the Chernobyl accident could actually be detected in North America. You can see here from a volcano, so this is the ash cloud, shut down air traffic in much of the northern hemisphere over Europe, Ireland, and into Russia. We can also talk about this in terms of, I've mentioned ozone depletion. And that affects the poles, but that also affects all of us. It wasn't at the poles where those CFCs were released. They were transported. We can talk about this in terms of climate change, the CO2 cycles. So when we look at air pollution, we can look at it from a local level. We can actually look at it from within a building level all the way up to the entire globe. And we'll do our best to cover much of that, but as you can imagine, it really is a field in itself. So hopefully that gives you some sense of the Earth's atmosphere, classes of pollutants, the scales of pollutants, and sources of pollutants.